Hello, this is my presentation for ASC 511 Earth Observation Remote Sensing. I'm Philip Orozco, and this is Satellite Precision Farming with UAS. So, precision agriculture gives farmers the tools that they need so they can go and fertilize, water, or help the crops wherever they need them. Precision agriculture gets rid of the need for intuition and expertise, and it gives precise data for the farmers to act up. Right now, the most common way to use precision agriculture is obtaining image data from either satellite or unmanned aerial system sensors using hyperspectral images. While there is no a lot of information between comparing the two systems, I hypothesize that there have to be little to no difference between the two resolutions between the two systems. So a statistical difference of p less than 0.05 in the average of the two resolutions of the system means that yes, there is a statistical difference between the two systems. At the end of the presentation, I'll give my recommendations to why unmanned aerial systems are preferred over satellite images now. So precision agriculture tells the farmer, hey, these are the trouble areas, go inspect over there, maybe need more nitrogen, maybe needs more water. Hyperspectral signature is the electromagnetic radiation that gets reflected or absorbed by different mediums, in this case plants. So my main point was what is the difference between these precise, highly technological asset that we have in the space. This one is the worldwide view versus a phantom tree with a little attachment. Can they both perform the same objective when it comes to precision agriculture? There is not a lot of information comparing the two technologies like this. There's a lot of information of either using satellites images or unmanned aerial vehicle images to produce precision agriculture images that you can use to identify different physiological changes on the plant, but there's not direct comparison. So my research question is, could unmanned aerial system replace a satellite hyperspectral imaging? And then my null hypothesis is that there is no statistical difference between the two resolutions. And then my alternate hypothesis is that yes, there is a statistical difference between the two resolutions provided by the two systems. For this research, I'm going to compare the resolutions offered by the two systems because at the end of the day, that's what you need to identify weeds, to identify where a plant ends, where the other crop ends. And according to my literature review, you need at least 10-meter resolutions to identify two different types of plants in the same crop. All the information I got from online sources, either the brokerage accounts or the space agencies that deploy the satellites, or the vendors that have the unmanned aerial system sensors. A little bit of information before we get there is that unmanned aerial systems, because they change the fly height, then the resolution changes as they go up and down. Of course, the higher ceiling is 400 feet thanks to the Federal Aviation Administration FAA regulations. Then we're going to use an ANOVA to figure out if there is a statistical difference. So the most important thing about hyperspectral imaging when it comes to precision agriculture, plants absorb visible light of the blue, green, and red band, or the 400 to 700 nanometers, and then reflect the infrared, near infrared, and the infrared band in the 700 to 1300 meters. Because of this, then we can compare the different band images obtained from the sensors, and then create what is called indexes, which is when you compare two images, superimpose one, subtract the other one from the other one, then you can create a new image that can be correlated to a physiological change in the plant. In this case, we're looking at plant health. And for plants, as you can see here in the bottom, the same amount of light is electromagnetic radiation from the sun is coming here to this plant. This is a healthy plant, so a lot of the red light is being absorbed because it's using the photosynthesis process. So chlorophyll, water, all these things, and light is used for the plant to grow. So a lot of red light being absorbed means that the plant is healthy. All plants reflect the near infrared light, so it doesn't matter how much light is coming, they're all gonna reflect about the same near infrared light. But on a healthy plant, because it's not doing photosynthesis, it's gonna reflect a lot of that red light, the red spectrum, because it's not healthy, it's not doing photosynthesis, it's not growing. So when you normalize it by subtracting the difference and dividing by the same amount of light being emitted to the plant by the sun. So this is what this equation means. It means this is the total amount of light coming to the plant, and this is the amount of light leaving the plant. Because of that, a higher value, closer to 1 on the positive, means a lot more light is being absorbed by the plant, and that's good. And value closer to -1 means that the plant is not doing so well. Or here we see an example picture. You can see the green means good, red means bad, and the farmer has to go over there and figure out what's going on with those plants. The data, as I say, gathered from these resources. These are either brokerage accounts or the space agencies that deploy the satellite. These are the resolution in meters, and this is the vendor data provided by the GSD ground, which is just the resolution of that sensor at 400 feet. I do a little bit of statistics to find out that these are follow the normalized curve. I found that the satellite follows the normalized curve, but the sensor data does not follow the normalized curve. Because this is representative of the population, it's not just a sample, then going on ahead and saying, well, this is just pretty much the population. This as many of the sensors that are out there that meet the minimum criteria. So we're gonna go ahead to the ANOVA, or analysis of variance, which pretty much looks at the mean between two, and we can say, well, this one looks bigger, and that means the resolution is worse in the satellites than the man-aerial vehicle. We have to use a statistical tool to be sure, and that's what the ANOVA does. It measures this, if there is a difference between the two means, and then it measures what is the chance that that difference is caused by random error. That's the analysis of variance. As we can see highlighted, the p-value, or the chance that the difference caused by random error, is less than 0.05%, which is our threshold over here. So we have to reject our null hypothesis and instead accept our alternative hypothesis that there exists a difference between the two resolutions offered by the satellite and by the unmanned aerial vehicles. What does this mean? Well, it means that when we were looking at the two resolutions, it is correct. It seems like the unmanned aerial vehicle sensors can provide better resolution. Of course, this happens because it's only 400 feet versus 1,000 feet above the Earth, like satellites are. But because of this, because of this, human aerial system has to pass over the same area multiple times and overlap the images to make that stitch, that panoramic image, where a satellite can just take a whole image of different multiple crop fields in one swap. And of course, we're only comparing NDVI index, which only uses near infrared and red light. Some of the other most different indexes analyze water and nitrogen on plants, use the blue band and, and different bands. So the satellite images might have an advantage if the manual systems only offer near infrared and red light. So I didn't take that into account, but it could affect depending on what you want to do. Other findings: some of the satellites require a minimum amount of images that you have to buy at a minimum of distance. So because of this and the findings, I recommend manual systems as part of a precision agriculture process for the farms. I just wish there was a lot more user-friendly software out there, because as it is now, it requires a lot of technical knowledge to take out the different bands, compare them, create the indents, and analyze the image. In the future, we want to know that you can use the 40-meter resolution Landsat or the 20-meter resolution Sentinel-2 hyperspectral data to create good enough images that you could just replace the other satellite data. And again, I hope all farmers out there start using more precision agriculture. Thank you.